Something that I want to dig into a little bit more on neuromorphic computing that I think is really cool is this idea that we talk so much today about how much energy a system like GPT-4, that kind of scale of model uses in terms of energy, in terms of water to cool the systems. It's so interesting to me to think that a neuromorphic chip done correctly, and it would probably take us a very long time, although maybe with AI we'll be able to get there faster than we think. You could theoretically have the power of a human brain running on the power of a light bulb. And we know that because that's how much energy the human brain uses. So it's theoretically possible that you could have all of the capabilities, this kind of, the benchmark that a lot of people say for artificial general intelligence, AGI, is being able to replicate the kind of intelligence that a human has. So if that's true, with a neuromorphic chip designed to replicate the way, much closer to the way our biological brain really works, you could get costs down in terms of energy costs down to something almost negligible.
Absolutely. So I think there's two areas where this could play out. Of course, obviously, most people would think about training these models, large language models, where most of the energy currently is consumed. But I would probably even go deeper into inference. So, the application of these models in daily lives, where it's about very cost efficient scalability in order to drive the right data into the right devices. That could be probably even a more beneficial area for driving neuromorphic architectures going forward. And still, given the fact that data transfer in these devices is kind of a key area for optimization, certainly. And I don't even think it's taking 10 years. I would say it's a 5 years plus question rather than a 10 years question.
You mean specifically there, like the five
for application of neuromorphic architectures in general compute.
Perfect. But it's probably not going to be down to human brain kind of efficiency. No, nothing
Not
anywhere
in
near
that
that
speed,
close.
but given the progress of how AI is found its applications in the past 3 to 4 years, if you just apply the same innovation speed going forward, I think we can expect quite a lot from AI in the next couple of years.
For sure. No question. Directly related to what you just said about being able to have less data transfer, get rid of that bottleneck in AI capabilities, where today a lot of the cutting edge AI that you want to have happen on your, say, your phone, your laptop, needs to be sent to a data center where huge servers with lots of NVIDIA chips or something like that are able to process the request and provide some generated output. That bottleneck could be removed, of course, as you just said, by having the edge device, the laptop, the car, the phone, be able to do that processing itself. And so, you've mentioned that the AI boom. You previously mentioned that the AI boom has so far been driven by data centers, but the next wave will involve AI chips running directly on edge devices. What are the biggest material science challenges in enabling this transition, and how is your company contributing to solving them?
If you start with what is currently being used in data centers, then it's all driven by further shrink of devices, getting more transistors on a die, and driving performance based on kind of lower voltages, less energy consumption. That's what we see currently happening with that enormous GPUs or GPU-like systems being used for training the large language models. Of course, with NVIDIA being spearheading that part. And already here you see all the different dimensions of improving performance already under kind of one umbrella. One is faster devices, more integration on a device based on EUV lithography, based on gate all around or nanosheet architectures on a device. That is like scaling with Moore's law on a specific device. At the same time, you see that already being integrated, memory and the GPU is being integrated in one integrated system called CoWoS-based system. This is a chip on a wafer on a substrate that is kind of bringing data and compute closer together. Already another dimension of scaling performance. That's already happening as we speak with these, take the Hopper or take the Blackwell chip that is driving the performance of AI-based data center applications. That is what's happening right today, as well as on device with the latest and greatest technologies on smartphones, in laptop computing or desktop computing, or even in devices like automotives, and in production systems.